Hello guys, hello everyone. Welcome to today's Yebo physics session. This is Part 1, Session 3, the session that you were supposed to have had last week on Thursday, but we couldn't have it then due to a few issues. But nonetheless, we are here. We are continuing with questions number 17 to 24 of electric fields. So if you are interested in electric fields from a continuous charge distribution, this is the session that we are going to cover that particular part. So I hope you will be able to contribute also and participate in this session and give your questions or your comments so that we can go forward and no one is left behind. So just give me a moment while I check my audio so that we don't have problems with the recordings for the benefit of others that will see these sessions later. So if you are live and you can hear me, I can see we have some guys that have joined us. Rotenda and Langa, you're welcome. Thank you for joining us. Please feel free to unmute your mics and comment if ever there is an emoji and a reaction from both of you. Thank you, guys. You are very welcome. So we're going to be looking at questions 17 to 24 today, continuous charge distribution. So if you would have any questions, you are free to just stop me in between and at least send that question in case I'm not able to read the chats that are in our chat boxes. So in case I miss something, please just unmute your mic and indicate. Okay, so I'll just go on with the question that's showing on the screen. I'm sure the guys on Teams can hear me. They just responded. If you are live on YouTube, please also show if you have a problem with the audio so that we rectify this as quick as we can. But anyway, the first question goes, a charge of 80 nanocoulombs is uniformly distributed along the x-axis from x equals to 0 to x equals to 2 meters. Determine the magnitude of the electric field at a point on the x-axis with x equals to 8 meters. So remember, with the uniform charge distribution, I'm not gonna go back to the basics, which is what you have done in the first two sessions, but already you have defined charge and given its properties. You know charges exert forces on each other, and those forces are given by Coulomb's law, which is the inverse square relationship. And charge is measured in coulombs. So we have 80 Newton charge in this case, but this is now distributed along an axis. So it's a distribution of charge. But you should also know that the electric field due to two or more charges is a result of superpositioning of the individual electric field from each charge. So when they superpose like that, they'll add up, and the adding up is basically a vector addition. So it's not scalar addition where you just add the magnitude of the field plus the magnitude plus the magnitude. Those are scalars. But in this case, it's a vector, meaning it has magnitude and direction. So we would use our components to resolve and get the resultant field at that particular point. So that's how the fields superpose. But now, when we're looking at a continuous distribution of charge, in this case, we have the case simplified because this is uniformly distributed charge. So it means we would have equal segments or amounts of a charge contributing to every point from the distribution to the field or to the space surrounding it. So with a uniform distribution of charge like this, we already know that if this is a linear charge distribution, like we are told it's along the x-axis, then the charge density is lambda, which is basically dq over dx or over dl. So it can be dl, which is the length. So we can use x in this case because it's along the x-axis. So that would mean, therefore, dq is simply lambda dx, and the integrals of these will simply give us q equals to lambda times the x. lambda times that x, which is basically the length of the linear distribution of charge, or of the line of charge. Okay, so now what does that mean? It means for a length of charge along the x-axis like this, we have, in this case, this is x, that would be y. Then we have small elements. So we can have small elements. Sorry about that. This is what I want, this one. That small element constitutes the charge, small charge element dq, and its corresponding length is dx. So it means if we add all small infinitesimal elements dq along this length, we get an overall charge q. So that is integrating along the x. Basically, that is what we are saying in terms of the total charge of this system. Same applies to the field. So if we want the electric field at this point, remember, for the electric field, due to such a distribution of charge, you had to assume you have a distance there, which is a, and the length of this whole rod being L. That would mean you simply describe your dE along the x, which is dEx, will be equal to, the simple equation there will be Q. Let me start with that equation anyway first. So we've got E equals to, if it's E1, is due to Q1 times KE over R, let me call that R1 squared. Remember, where does this come from? If we have got E1 is force 1 per unit charge. So why I used Q2 in this case, this is the force on Q2 due to electric field or due to charge Q1. So basically this is the electric field E1 will therefore be the force per unit charge, where the unit charge is the charge that is introduced into the electric field of Q1. So E1 will generally be the force per unit charge like that. So remember, we said this is from Newton Coulomb's law. F1 will be KE times Q1 Q2 over R squared. So this will be R12, the distance from Q1 to Q2. And as such, if we divide both sides by Q2, we have F1 over Q2 being in terms of Q1 alone. Force per unit charge on Q2 will be K1, Q1 over R1 squared. So it can be 1, 2, 2 can be the point at which we are measuring the electric field. So from Q1 to the point of measurement of the electric field, where ideally we will have our Q2 experiencing that same force. So this is the value for the electric field at a given point due to charge Q1. So now when we are looking at the continuous charge distribution, our dEx in this case is given as Ke, still the same, dQ over R squared. Okay. So what we want to see, we want to see how this electric field at any point along the x would vary. So which means we have our small dq elements contributing to that point which is at x. So in this case, this point at x is will simply be an integral for the charge along the x, which is, so we represent our dq according to, where is this? according to that equation as lambda dx. So already we now have a variable of how dq varies with x. Everything over, because the other variable is this x squared. Everything is along the x. So we've changed the variable from dq and how it varies with the distance where the dq is influencing the electric field at the point of measurement along the x-axis. So this integral, it would mean that if we do an integral of dEx, it will give us Ex, the electric field in the x, and this integral is from the point A to the point A plus L. So if you do that integral, this is dx over x squared, x to the minus 2. If integrated with respect to that, will give us 1 over minus 1, x to the minus 1. So this is ke lambda, which is constant, times negative x to the minus 1 from L plus A. So remember, I was saying L plus A because this is A where we have our rod, and this is L plus A, the which is marking the end of the rod. So this is all the charge elements that contribute to the overall charge through the length of the distribution. So from A to L plus A, which is ke lambda minus 1 over L plus A minus negative 1 over A. Is that supposed to be a comment? Okay, I see more guys you have joined there. Hope you can see where we are so far and you can follow. Welcome, nonetheless, welcome to you all. You've been muted. Okay, can you see where we are so far? Can you follow that integration? Tell us what you get from that evaluation. What is the final solution for us here? What will be the final solution? Can someone give us our final expression? Anyone is welcome. Langaro Tenda, Minenhle, Avene, Samuel, Nkosibonke, Sive, Chehofatso. I hope I pronounced your names right, but yeah, welcome guys. Just tell us what you think. What do you think we do from this stage? Or if there's anything you don't understand from where we started, you are free to say it out.
Can you replace the lambda with Q over lambda?
Sorry, come again. I think I didn't get that clearly.
Don't you replace the wavelength with Q over L?
Good. Okay, that's perfect. So we have to replace this lambda with Q over L. That's good. Thank you for that contribution. So that means if we evaluate also the part in the bracket, this is Q over L. I'm sure you know where that is coming from, which is basically rearranging this part. So you have Q over L there. And this is negative and negative will generally give you a positive. So you have 1 over A minus 1 over L plus A. And if you can evaluate that into one fraction, this should give KEQ over L multiplied by A multiplied by L plus A as a common denominator. And this gives us L plus A. A into that is L plus A. A into the denominator gives us L plus A, which will multiply by 1. We have L plus A minus L plus A into that, it's A multiplied by 1, it's A. So this A, that A cancel out. what we remain with is L over A plus L plus A. And because we have L there at the top and at the bottom, this L cancels that L. And we have finally KEQ over A L plus A. So this is our final expression for the electric field along the X. This is how the electric field along the X varies. So now that's basically to show you where this uniform charge distribution is coming from, and that should help us answer this question number 17. So on question number 17, our Q, so don't forget this expression, this equation, it's a very important equation that we are going to be using. So what is Q in question number 17? The given quantities. Q is 80 nanocoulombs, right? Then the distribution is from x equals to 0 to x equals to 2. So in this case, our L is equal to how many meters? How many meters will that L be? How many meters is L? Anyone?
20 times.
That's how many meters? Sorry, I heard someone speak. What was that? From x equals to 0 to x equals to 2. So the distribution of charge is from x equals to 0 to x equals to 2 meters. So that means our L is, that should be simple, guys.
2 meters.
2 meters, thank you. It's 2 meters. So we have a 2 meter length of our distribution of charge in this case. And now we want to measure the electric field at a point on the x-axis when x is 8 meters. So in this case, the point of measurement, x equals to 8.0 meters. But according to our derivation here, where is the diagram? For this diagram, what we're measuring is the electric field at this point. It's the electric field at P, which is basically at the origin due to this uniform distribution of charge. So that means A becomes the distance from the point of measurement to the rod. So what will be A, in your thinking, what will be the corresponding A for us to apply this equation to the question? What will be A if the rod is starting from x equals to 0 to x equals to 2, and the point of measurement x is at 8 meters? What is A? So the orientation has just shifted to having a rod there and measuring at point P there. That's how different this question has been formulated. So you have L up to that point, from 0 to that point, then you have that distance which we are calling A. So what is A? Yes? Feel free, there's no wrong answer. It's good to just give attempts. What do we put?
6 meters.
6 meters, very good. So 6.0 meters is A. A is the distance from the end of the rod to the point of measurement. So that's how we have made that derivation. So now with our expression E equals to KE we know KE. Did I list KE there? So let me put KE here as part of our quantities. 9 times 10 to the 9 with the units. That should be, I think, farads per meter or something. But anyway, I'll leave the units out for this one in the meantime. And that means our electric field KE times Q over A, L plus A. Can we substitute those values there and find E? What value of E do we get? Excuse me. We've got Q 80 nanocoulombs, which is 80 times 10 to the minus 9. L is 2, A is 6, and KE is 9 times 10 to the 9. What do we get for E?
It's 15.
It's 15. Wonderful. Thank you. We have 15 newtons per coulomb. So E is given in newtons per coulomb. So that is the 15 that we see there in B. That's how we get to 15 newtons per coulomb for this question. Thank you for that contribution. Any questions regarding this? Are we all happy? Okay. All right, so we are gonna proceed to the next. So that was 1.5 times 10 to the power 1 by Minenhle. Thank you for that. I can see you typed something there. Okay, so the next question, question number 2, or number 18, it's the second for the day, is this one. A charge of uniform linear density, 9 nanocoulombs per meter, is distributed along the x-axis from x equals to 0 to x equals to 3 meters. Determine the magnitude of the electric field at a point on the x-axis with x equals to 4 meters. Can you attempt this one? It's more or less the same question, just different values put there. How would you calculate that one? You can even lead me while I write for you, or otherwise you can work it out and give us the answer. Everything is still fine. So if anyone wants to tell me what to do so that I follow instructions from you, I would appreciate. So just list what are the given quantities for this question. It is important to list these so that we know what we want. Yes? I'm listening.
Okay, we have the charge.
The charge, yes. Well, what are we given? Okay, sorry, this is linear charge density, eh? So the charge should be linear charge density times L. So this one not given directly. Let's put a question mark. So where do we start here? Saying we have A. Linear charge density, we agree?
Yes.
Yes, linear charge density, good. What's the value? Yeah, you're doing fine. Continue, please continue.
I don't know if it's a 90 or a 9.
Okay, sorry, my screen could be too small for you. It's 9.0, yes, nano coulombs,
10 to the power minus
which is times 10 to the power minus 9 coulombs per meter. So already if you see that unit or the term itself, it tells you this is just not charge, it's the distribution of charge per unit distance, which is a charge density. So that's the charge density, the lambda, or yeah, our linear charge distribution. What else do we have?
We have the length.
We have the length. So what is our length?
3 meters.
It's 3 meters. So you can see the length is from where the distribution starts to where it ends, from x equals 0 to x equals 3, which gives us 3 minus 0 is 3 meters. What else are we given? What else do we need to highlight in the quantities? Do we have A? Do we have A?
Yes, we do, sir.
Yes, what is A?
It's 1 meters.
1 meter. Thank you so much. A is 1 meter because we are measuring the electric field at x equals to 4 meters, and the distance between that point of measurement to the end of the rod will be 1 meter. 4 minus 3 is 1 meter. Perfect. So now the equation, remember the equation for the electric field along the x. So this is our golden equation for the day. That's our golden equation for the day, coming from where? From here, KEQ over A, L plus A. That's why we said we want to find A, want to find L, want to find Q. So can you guys please give me what the electric field at that point, 4 meters on the x-axis, will be?
Sir,
Yes.
please try adjusting your screen.
Oh, okay. Let's see what's happening there. Okay. Thank you for notifying me. Let me see what's happening. Okay, I see. Right. Okay, I think everything is in perspective now. Thank you for that. Thank you very much. Okay, so there we are. Ex is Ke, with the value of Ke is that constant, which we didn't list there. We can as well edit 9 times 10 to the positive 9. Multiplied by Q. The Q is lambda L, so I was just trying there to multiply lambda, which is what we have there, times L, which is 3 meters. So I'll put the 3 there, over A, which is 1, L plus A, which is 3 plus 1. You can evaluate that. You can evaluate that.
It's C, sir.
It's C, 61.
Yes, sir.
Perfect.
Because it's 60,75.
Okay, thank you. That's very correct. So we've got 60.75, which gives us a rounded value of 61 newtons per coulomb. So that should give us lead us to that solution. Perfect. Any questions so far? I hope we are all good thus far. The next one is question number 19. Which is this one. So we have a charge of 25 nanocoulombs uniformly distributed along a circular arc of radius 2 meters, which is subtended by a 90-degree angle. The question is, what is the magnitude of the electric field at the center of the circle along which the arc lies? So we have a different distribution this time. It's a distribution, let's see if I can simplify it like this. If this is our x-axis, then maybe 45 this way and 45 that way. Is that 90? No, it's not really 90, but anyway, it's more of an estimate. Okay, so we have 90 degrees there, something like that. Then this is our distribution of charge. Let me give it a different color. Okay. Now the charge on this distribution, Q, is 25 nanocoulombs, right? And it's uniformly distributed, so which means we can even talk of the lambda there being Q over L, but we know that the length of this arc is given by what is this? Is it pi times radius? Remember the length of for the whole circle, that length will be 2 pi r. So that's r theta. So we'll call it r theta, where theta is in radians, for theta in radians. If theta is in radians, then that length is r theta. So if the theta is 2 pi, which is the angle on a circle, then you have got your 2 pi r, which is the formula for the perimeter. So it's 2 pi r, or pi times diameter. So in this case, since theta is in radians, this theta will be pi over 2. You've got this giving us pi over 2 times r for the length of the arc. But anyway, what is important is the knowing what the value of the electric field at that point is. What is the magnitude of the electric field at the center of the circle? So the center is point O, and the electric field, in which direction is the electric field at that point? In which direction is the electric field at that point? So it doesn't matter whether the charge on the distribution is positive or negative. There's an axis upon which this electric field would lie. What do you think that is? Anyone?
I think it will lie on the x-axis.
Very good. It will lie on the x-axis. Why is that? How and or why? Or can you explain further? How did you get to that conclusion?
On the y-axis, they are going to cancel each other.
Yes, along the y-axis, they will cancel out. Remember, each component, we talked about infinitesimal, least small components, each contributing to the total electric field at a point, and these electric fields will superpose at each time. So if we take a small element, dq, maybe that element there, it contributes to an electric field that passes through that point in that direction, and we'll call it E. So that's the small element dq, and its radius is also, its circumference is, we can call it r d theta, because it will actually also have its own small component of the angle theta. So this is dE, let me call it dE. And it will mean that the total electric field, remember there's another component anyway here, which is also from a dq counteracting in that direction, and it will have also a field dE, but in that direction. So we can say that this dE1, this dE2, but both have components along the y that are equal but opposite, so they will cancel out, but those along the x will add up and give a resultant field in the x. But anyway, if we consider each element has got a field dE, and Ex will therefore be dE cos theta. Do we agree? dEx, let me call it dEx because we are adding all these components. Are we together on this one? Components. Where are these people? Are you still there, guys? Okay, good. Confirmation from Samuel, so we can continue. So if in this case, if this dE component is an angle theta, so that's the theta that we'll consider there. It's the same theta there, so dE cos theta is along the x. Okay, so if that's dE cos theta, that means this is, we said dE is KE dq over r squared cos theta. But remember, we said in this case our dq, we have to express our dq in terms of the variable component that is summing up within this expression. So in this case, our radius is constant. What is varying is dq along the circumference, which is similar to a variation along theta. So we have to express dq in terms of theta, and as such we have said in this case we have lambda equals to, or let me say dq equals to lambda dl. So our dl in this case is basically this part, dl equals to r, which is constant. Dl varies with d theta. If because r is constant on your radius, if you have a bigger circumference, it's because of a bigger sweep of the angle from the center of the circle. So which means this dq can be replaced with lambda times r d theta like this. So therefore we have ke, we replace dq with lambda r cos theta d theta. We now have a variable which varies with the angle, everything over r squared. Then we can eliminate that. It means for our ex, so this is dEx, we can integrate giving us ex, and ke lambda is constant over r, everything is constant there, integral of cos theta d theta from 0, angle is 0 to 90 degrees, so from 0 to pi over 2. So ke lambda over r. What is the integral of cos theta? It should be sine theta. Cos theta comes from the derivative of sine theta, so we're just reversing that. And sine pi over 2 is 1, sine 0 is 0. So this is ke lambda over r sine pi over 2 minus sine 0. Sine 0 is nothing. Sine pi over 2 is 1. So that's 1 minus 0, which is ke lambda over r. So this is the expression for the electric field due to this linear distribution of charge that is bent into a 90-degree, an arc subtended by a 90-degree angle. So this is our formula. That's how we get to that formula which we have to use for this particular expression. So I just didn't want to get to the formula. If you are not interested in the derivation and where it comes from, it's still okay. You should at least know what formula applies where. But it is also very important that you know that for a continuous distribution of charge, what we have to do is express at least the variable dq in terms of the varying quantity within the distribution itself. So in this case, it can't be with respect to r or with respect to x, because x is at this point equidistant from the distribution itself. What is changing is the angle. So ideally, you want to express your dq in terms of a variable, or what we call an operator, a d theta operator. So you have to know some of these things to say your L, in this case relating to r d theta, will give you at least your change of variable that can enable you to at least express the electric field at that point in a simple fashion like this. So now that we have Ex, we have given quantities which we can list here. Let's see the question again. The quantities, the charge is 25 nanocoulombs. So given quantities. We have Q 25 times 10 to the negative 9 coulombs. That's number one. The arc is radius 2 meters. Radius is 2 meters. And the arc is a 90-degree arc. So the circumference, circumference L, we said is r theta, which is 2 times pi. Theta is in radians, pi over 2. So that simply reduces to pi for the value of L, which is the length of the arc. And therefore lambda is Q over L, which is 25 times 10 to the minus 9 over pi. So you've got that expression there, Ke 9 times 10 to the 9. I think I'll end there. The formula, the electric field at a point at the center, which we have said in this case can be along the x, depending on the orientation anyway, is equal to Ke lambda over, that's Ke lambda over r. So expressing that, 9 times 10 to the 9 multiplied by lambda 25 times 10 to the negative 9 over pi, Ke lambda over r, which is, I think r is 2. Evaluate this for us, please. evaluate this for us.
Do you have 36 there? Because I got 35,81.
35,81. I think that's the correct one. 35,81 should be the correct one. It's actually C here is 2 times that value. So yeah, we don't have that value here, but that is the correct answer to use there. 35.81. And what's your unit? What will be your unit?
Will it be Newton per coulomb?
Very good, Newton per coulomb. So it is important not to leave out the unit. So that's Newton per coulomb. It's force per charge. So that would be Newton per coulomb. Or you can use the volt per meter. It's still acceptable. 1 Newton per coulomb and 1 volt per meter are the same. So you have, in this case, 35.81. So this, I'm sure this answers, like this 71, you'd get it if we had a semi circle or a half angle. If this was completing into a half angle like that, and you would measure the field at the same point, then of course the orientation of the field changes to a different direction, but the overall becomes 71 Newton per coulomb, because in the equation it will therefore have 2 ke lambda over r. So that 2 ke lambda over r is for a semicircle, not for a quarter of a circle. Okay, question number 20. Question number 20. A uniformly charged rod, another charged rod with a charge per unit length of 3. Length is 2 meters, charge per unit length is 3 nanocoulombs per meter, is bent to form a semicircle. What is the magnitude of the electric field at the center of the circle? Okay, I've already given you a hint on this one. So you guys can work this one out and give us the answer. You can work this one out. Remember, we're dealing with a quarter of a circle. This is now a semicircle. It is just twice the size and twice the effect. So you have to be careful with the L and the R and what you are using in this part of the question, the lambda and the Q. So lambda is Q per unit L. Then R is radius, L is circumference, or just a segment or portion of the circumference. So those variations are important to note. Do we have any further information? We know Ke is always a constant.
sir.
What do we have?
Can you please repeat the question? We didn't get you.
Sorry?
Can you please repeat the question?
I'm not getting the question clearly. Do you want me to repeat the question?
Yes.
Okay. So the question says a uniformly charged rod has a length of 2 meters and the charge per unit length is 3 nanocoulombs per meter and is bent to form a semicircle. So this time we have a semicircle like that. And the question is, what is the magnitude of the electric field at the center of the circle? So what will be the magnitude of the field at that point? So what I just said is we have already looked at the equation for the quarter of a circle, which is this one, Ke lambda over R. So our E is equal to 2 Ke lambda over R. This is the expression for the electric field at the center of the circle. So now the lambda were given, the L were given, the Ke were given, the angle theta is pi. So all the information is there. We just need to apply it to that equation. What we are not given directly is the R, but we are given the length, which is the circumference. This one. If straightened, it gives us a length. And in terms of its arc, it is basically R times theta, which is pi. So you can find R in terms of L and pi from there and substitute into that equation and give us the E. Is that better?
Yes, sir. Thank you.
Good. Welcome.
So, sir, for this, does it mean for the R we're going to use I over length?
Come again?
For the R, are we going to substitute using pi over, length over pi?
Yes, yes, exactly.
The answer is 85.
85.
Yeah, 84.8, which is 85.
Wonderful. Okay. Do we all agree? Did we all get the same thing, guys? I think 85 is D there.
I don't agree, sir.
You
I don't
agree?
understand.
Okay.
Yes,
yeah,
there's something that I think I'm missing. On the lambda, aren't we not going to divide the 3,0 times 10 to the power negative 9 by pi, then multiply by 2?
According to the question, lambda is given as is charge per unit length is the lambda. So the 3 times 10 to the minus 9 is used as is. So you don't need to divide it. Remember, when we put the quantities, we put lambda like that. So your lambda remains as 3 times 10 to the negative 9. Do we agree?
Yes, sir. Thank you. I understand now.
Okay, good. So we have this over r, where r is L over pi, which is 2 over pi. These 2 and that 2 cancel out. This cancels with that. And that's giving me 27 pi. Let me just cross check one more time, but I'm sure it's the 85. I just need to be sure we're on the same page. 27 multiplied by pi. 84.8. Perfect. Thank you so much for that nice answer. It's 85 and that's correct. So that's 85 newtons per coulomb. Is that a comment question? I might have disturbed you while you were saying something. Or can we proceed?
Yes, sir.
Yes, sir.
Okay, good. So the next part is I don't think there are calculations there. Anyway, this question is more of an analysis of what you call them equations, or the expressions that we would get from the continuous charge distribution. And for this question number 21, a 16 nanocoulomb charge distributed uniformly along the x-axis from x equals to 0 to x equals to 4, similar to the type of questions that we had when we started. Which of the following integral is correct for the magnitude in newtons per coulomb of the electric field at x? Something is missing there. What do I do? Okay. So it's okay. It says at x equals to plus 10 meters on the x-axis. Which is the correct expression? Which of the following integrals is correct for the magnitude in newtons per coulomb of the electric field at x equals to 10 meters on the x-axis? Clue. I'm sure if you have been working out or writing something down, you have an equation similar to this one here. Where is that equation? Something like that. Okay. So you have an equation like this. The integral we had earlier was that, just for your clue. So already the charge is a 16 nanocoulomb charge. And what else do we want there? To express KE, KE has been expressed in numbers. So you have your 9 times 10 to the 9 expressed there. And your lambda. Do we have a lambda for this system? Yes, we do, because we have charge per unit length. So our lambda is 16 times 10 to the negative 9. And the length is, what is the length of this distribution? So we're evaluating the constants basically. We're evaluating the constants. Our constants are KE lambda. So dEx, let me just write it neatly for you. We have d of the electric field along the x equals to the integral from a to L plus a of KE lambda dx over x squared. X plus, what did we say there? Was that just over x squared? Yes, like that. So this is the expression KE lambda dx over x squared. So with that, the KE lambda is a constant that we need to evaluate. What are our limits? So what are our limits in this case? the limits are governed by the length of the rod, because we're integrating dq elements along the rod. So in this case, the limits are from what to what? While you're still thinking, ke 9 times 10 to the 9, and lambda is q over L, which is 16 times 10 to the negative 9 over L is from x equals to 0 to x equals to 4, so it's over 4. Then we have dx over x. In this case, we are not going to just use x squared. We have to evaluate this in terms of a. We have to evaluate this in terms of a. So what are our limits? What are the limits? In other words, in what zone or region is the rod extending, or the distribution of charge extending? The question simply gives us it's from x equals to 0 to x equals to 4. So we've got 0 to 4 there. Those are our limits, right? Then if we remove the powers that are minus 9 and plus 9 cancel out, because this is 10 to the 9 over divided by 10 to the 9. So that's 1. 4 into 16 is 4. 4 times 9 is 36. So we've got a limit from 0 to 4 of 36 dx over. So the point of measurement in this case, remember, we have our point of measurement in this case given as 10 meters. So that 10 should be appearing in that expression there as 10 minus x squared. So the length A, in this case, the distance from the end of the rod to the point of measurement is 10 minus x. That's the distance from the end of the rod to the point of measurement. And that distance is squared there. So this is only representing or giving us an estimate of this distance A, which is the point of measurement to the length of the rod. And in this case, this was multiplied only by L plus A. So the estimate is simply to say if A is greater than L, then it means A plus L is approximately equal to A. So we've got A squared in this being used for this expression. So I'll repeat, we got this expression here. A was basically similar to the point of measurement minus the point of the end of the rod. So that distance that we have always been measuring in this expression, when we had all these values, we had a point of measurement x, which was 4 in this case. X was equal to 4 meters, and L was 3, then A was 4 minus 3. This is the same thing that we are using here to say x is 10, or point of measurement is 10, and x is any point along the length of the rod until we get the whole length of the rod, which is only up to 4. So 10 minus whatever x is contributing to the field is going to be integrated to give us that distance squared. So that expression is basically what we have in A. So there's nothing, I've already done that whole thing there to give the expression for this integral. So the integral of dEx is only Ex. That's the electric field expressed in integral form for a measurement of the field at a point on the x-axis, which is 10 meters. A similar question is following. The question is, any questions? Do you guys follow? Is it making any sense?
Yes, sir, it's making sense.
Very good. Thank you for that affirmation. So the next question here is similar. Can you attempt this? A uniform linear charge, 2 newtons per, I like newtons, 2 nanocoulombs per meter is distributed along the x-axis from x equals to 0 to x equals to 3. So the limits are already shown there. It's the same thing. Which of the following integrals is correct for the y component of the electric field at y equals to 4 meters on the y-axis? So this is now a different story. This is now a different story. Remember, for this, the orientation was rod along the x-axis, field being measured along the x-axis. But this time, you have the distribution along the x-axis, like that. Something like that. From x equals to 0 to x equals to 3. With a lambda of 2.0 nanocoulombs per meter. That's the density along that axis. Let's see. So we actually have our rod there. Yeah. Okay, so this is the charge on the x-axis. And now find the following integrals for the y component of the electric field at y equals to 4 meters on the y-axis. So we want that's 4 meters, that's 3 meters, and want the field GQ contributing to that point there. So this field is DE and its component along the y is that field there, DE cos theta. So now if we have this as our x, this as our y, then this is root x squared plus y squared, which is our r, the distance from the dq element to the point of measurement. Let me use small r. So the component in the y, dEy, equals to dE cos theta, which is equal to Ke dq over r squared cos theta. Okay, so remember we know our expression for the electric field is Keq over r squared. So I'm just replacing dE with dq in that expression. The cos theta already is because we're considering that component. But now what is if this is our theta, then cos theta, what is cos theta? Is adjacent over hypotenuse, which is y over r. So this is Ke dq times y over r. This is over r squared. So this becomes Ke dq times y over r cubed. And therefore the integral in this case is in terms of dx. So we express our lambda in terms of dx lambda. Dq is equal to lambda dx. So we replace change variable there. This is, so I'm gonna do two things here. Replace r with this expression and replace q with lambda dx. So we have Ke lambda y dx over, so dq with lambda dx, which is lambda dx, the y is already there. R cubed is root of x squared plus y squared, everything to the power 3. So this is Ke lambda y dx over x squared plus y squared to the root of 3 over 2. And this is therefore integrated ey will therefore be the integral of that. Okay, so what is in this case we can now substitute for the constants. The constants are values like y. Y is at 0.4 meters on that axis, so y equals to 4. Ke 9 times 10 to the 9. Lambda, are we given lambda? 2 nanocoulombs. 2 times 10 to the minus 9 per meter. And y is also 4. Y is there again, which is 4. Ke lambda y, those are the different things that we need to express, and for x is varying from 0 to 3. So ey is therefore equal to 9 times 10 to the 9 multiplied by lambda 2, let me use brackets, 2 times 10 to the negative 9 multiplied by y, which is 4, then the integral from 0 to 3 dx over x squared plus y squared, which is 4 squared 16 to the power 3 over 2. Do we have anything of that sort? 10 to the 9 cancels. Okay, let me use a different color. This cancels that. Then we've got 9 times 8, which is 72. So that's this, and 18, 72, and 72 in there. Do we have an expression like this? That's A. That should be A. So it's the same principle. The same principle, what we have simply done is knowing this equation, we know that if we are to find the electric field at point P, at point of measurement P, then this electric field is contributed to by all the dq elements integrated along the x. So which means already we should express our dq as a variable with operator dx. So that's all we want to do. And every other quantity that is not constant, which means every other quantity that will vary when x varies. So the quantities like theta changes. In this case, when you are here, theta is 0. When you go to infinite, theta is approaching 90. So if you have cos theta, it means this cos theta should be part of the system that will be integrated, because it varies with x. So that's also something, one way you know it's not a constant. That's one way you know this is not a constant. So only if that is a constant. Our r is also a variable with x. So we express everything that is x, put it in terms of x, and get an expression. That should be a simple way to think of how to get expressions for these uniform charge distributions. Okay, I'm now tired, and I was still on question 23, but anyway, it's not a calculation, it's another expression, which is quite simple. So it's just 2 more questions, guys. Is it? Okay, I think I was supposed to go up to 24, but anyway, let's see. I think I'll finish in the coming 10 minutes, we'll be done. So charge Q is distributed uniformly along a semicircle of radius A, which formula below gives the correct magnitude of the electric field at the center of the circle. So we've already done something like this. If you can refer to what we have done and please give me an expression, I'll be very, very happy. Yeah, something like this. There is our expression there. So a charge Q is distributed uniformly along a semicircle of radius A. So our radius is A there. Which formula gives the correct magnitude of the electric field at the center of the circle?
I think it's D.
I think it's D2 KE, which is there. Lambda is Q over R is equal to, okay, this is over L, so L is R pi. Okay, so lambda equals to Q over R pi. So we've got an R pi there, which is A pi, and another A at the bottom. Thank you. That's very correct. So we replace lambda with Q over L, where L is A pi. So Q over A pi gives us 2 KE Q over A pi multiplied by another A, which is A squared pi there. So pi A squared. Very good. That's perfect. You have made it very simple for us. Thank you for that. D is correct. I hope we all agree on that. If you missed something, please just indicate so that we, will this thing go to the next page? 24. Okay, lucky me. So that we can explain it further, but I think it's quite clear. We've derived this formula. We've also seen how we get to it and substitute for the circumference. Two charges of 15 picocoulombs and minus 40 picocoulombs are inside a cube. Already this is Gaussian, but anyway, I'll just introduce. This is about Gauss law. I'm sure you've done Gauss law, so it's an interesting question. 15 picocoulombs and minus 40 picocoulombs are inside a cube with sides that are of 0.4 meters in length. So it's always nice. I like diagrams, so I would draw diagrams for myself so that I get at least a picture of what's happening. And at least in the meantime, I'll be brainstorming. So that's a cool technique. Anyway, the two charges are a 15 picocoulombs, and the other charge, which will be in a different color, is negative, and minus 40 picocoulombs. Pico is 10 to the minus. Pico will be 10 to the minus what?
12.
Okay, perfect. You're right. Pico is 10 to the minus 12. Thank you for that. So now this is to determine the net electric flux. Flux is phi. Okay. Anyway, I haven't said anything about flux, so now I'm being forced to start with this. What is flux? What is electric flux? What do you think is electric flux when you say flux? What will this electric flux be?
It's the product of the magnitude of the electric field in the surface area.
Okay, product of electric field and surface area, like this, as basically as vectors, right? Dot product. So they give us the electric field is a vector, and we consider the normal, the unit vector normal to this area to give us also a, making it also a vector perpendicular to the area, and therefore in this case the two vectors will make a dot product that gives us a cos theta component in a way. So it's EA cos theta. That's what we have. So this flux is basically the number of electric field lines. Maybe if I can put it physically, it's the number of electric field lines. So if we talk of flux density, we say flux over the area gives us E. So this is number of field lines per unit area. It gives us this electric field that we're calling field intensity or just electric field. It is the number of those field lines, which you say for a positive charge, these field lines are like this. Sorry, the lines don't bend, but anyway, you know, drawing is not easy. But anyway, these field lines from a point charge, right, go outwards radially like this. So in the area so close to the point charge, the unit area is small, but the number of field lines, you've got 2, 4, 6, are 8 field lines per this unit area. The flux density is higher. That's why the electric field is higher closest to the center or to the charge itself, because you've got more field lines in a small area. But the more you go outwards, like if you take this same area and put it here, you now have only one field line passing through it. So the flux density is now reduced within this area number 2. Right? And if we take an even bigger area, the same 8 field lines on a bigger area constitute a smaller flux density. So the electric field strength is what we call field strength is ultimately also the electric flux density, the number of, or the flux per unit area, number of field lines per unit area. So it's the flux per unit area. So that's basically what we are talking of. We're now looking at flux. But anyway, back to Gauss' law. It was just to at least so that you are comfortable with these terms. They shouldn't be something out of this world. Right. The idea with Gauss' law is that the electric flux is directly proportional to the enclosed charge. So if we take a Gaussian surface, right, in this Gaussian surface there, we can enclose that charge and have the electric flux. Let me use a different color again. Have electric flux in, so that will be a Gaussian surface, which is just a surface surrounding the charge. So if we take the charge out, there's no flux in there. The moment we put the charge, no matter what its position in this sphere, the number of field lines out through the whole surface of this Gaussian surface will be the same. So that flux will be directly proportional to the enclosed charge, Q. We'll call it Q enclosed. And the constant of proportionality is E naught. So phi is equal to Q enclosed over epsilon naught, the permittivity of free space. So now we have this setup now, a cube. So regardless of what the shape of this Gaussian surface is, we want the flux through the surface of the cube, which has 6 faces. We don't care what the shape is or whatever, but we just run to this Gaussian, Gauss law, the Gaussian expression, which says the flux is directly proportional to the enclosed charge. So the enclosed charge, total enclosed charge in this case is 40 picocoulombs plus 15 picocoulombs. Did I get those? Positive and negative with their charges. Because remember, if I put a negative charge here, a negative charge, some of these fields are terminating there. And some of these fields also would also maybe terminate there. And this one is now more of a sink. It is now more of a sink. It changes the whole picture. The number of field lines through this surface, we subtract what goes out, what is going out. What is going out being a positive, what is coming in due to the negative charge being the negative. So already the number changes. In this case, initially it was 8, everything going out over the area. Now you count what is going out, 1, 2, 3, 4, 5, 6, and what is coming in, 1, 2, 3. So you remain with a net flux, phi net, of the number of field lines. In this case, I've said it's 3 out of the initial 8. So 3 over the area, something like that. That's how it reduces from 8 over the initial area to 3 over the initial area. That's ideally what is happening here. So net enclosed charge we add the sum of the 15 and the minus 14, and the E naught is 8.85 times 10 to the negative 12. So you give me an expression for that and we are good to go. 40 minus 15 should be negative 25 over 8.85 times 10 to the negative 12. What do you get? Picocoulomb, so times 10 to the negative 12 as well.
Negative 2.82 times 10 to the power.
Thank you. You have just given us a good ending to the day. Negative 2.8 newtons per Newton meter squared per coulomb. That's how we get this flux. Negative 2.8 times newtons meter squared per coulomb. Like that. Was that simple? I'm sure it was, eh? So guys, have a good day. If you don't have any questions, but if you have questions, you are free to ask in the next 2 minutes before I call it a day.
Okay, thank you. So I would like to ask if tomorrow, at what time will be the tutorial?
So the tutorial will usually run from 2 to 4. But if the tutor that will be running it communicates otherwise, then they'll let you know whether it starts earlier or even later. They'll update you via emails. But the normal time is usually 2 to 4. Yeah, the general time is 2 to 4. So if it's not communicated otherwise on email, you should just check us on the platform every time at 2 if you haven't got any notification or email to say otherwise.
Okay, sir, thank you.
Thank you very much. Thank you for being on the platform, guys. It was nice and awesome having you around. You made it quite lively, and I hope you also benefited something from the whole thing. And have a good day. I'll stop the recording. If you have those who will have missed everything or anything, you can revisit on the recording or on our YouTube channel. The same stuff will be recorded there. Otherwise, all the best with your studies and enjoy the rest of your day. Bye-bye.
Thank you.
Thank you. Bye-bye.